Okay. I had to make sure everything is set up properly. Hopefully it is now. So let's do this again. I want to talk about the square trick. So what is the square trick? It's a way of moving the line, the predictor, closer to one of the points. How do we do this? So before that, we used the simple trick. And the simple trick did the following. When we had, let me maybe draw this. I have the y coordinate, and I have the x coordinate, and let's put a line here. So let's say this is our line, and here is our real price, and down here, so this is the price, and this is the predicted price. So in the simple trick, when the point was above the line, what we do is we add a small amount to the y-intercept. But when it's below the line, we can, the point can also be below the line, we subtract a small amount. Okay, I have this here, right? Yeah, I do have. So again, I have a line, and the line goes something like y mx plus b. M is the slope, b is the y-intercept, x is the input. What else? We have the real value, and this here, the y hat is the predicted value from the line, and y is the real value, like the point we are trying to fit. So the whole idea behind this is how can we move the line so that it gets closer to this data point? So it can get closer to this data point. Also, it can be below it. Let's say we have a case in which it's below. In this case, we want to move it down. We had, before this, we had the simple version. So if the point is above the line, we increase the y-intercept b. If we increase the y-intercept b, we are going to move this line right here up or down. So depending on where the point is, we increase the y-intercept or we decrease the y-intercept. And we adjust b based on whether the line is too low or too high. So this works, but it involves, it's manual, and it involves a lot of if-else logic. For example, I can say price is above b plus equals, I don't know, this small, why am I writing this so small? All right, otherwise I'm subtracting b for this from this small amount. Okay, now, but we should have also a smarter version for this. So instead of using if else, what if we use a mathematical trick that gives us the direction and the magnitude of the update automatically? And it can do this using signs. How it works. So, I forgot to tell you, I'm a bit sick, so apologies if I keep coughing into the mic. So how it works? If the point is above the line, so if, let's say this is y and this is another y, even though we shouldn't have two y's, but let's say, so we have two cases. If y is above y prime, so what do we have? We have an error, right? If this is 4 and the real value is 2. 4 minus 4 minus 2 is we have the error which is positive because we want to, and we calculate the error, sorry, by subtracting y from y minus. For example, here we will have 1 minus t, 1 minus 2 is minus 1, the error will be negative. Okay, so if y is greater than y hat, error is positive, right? Otherwise, if y is less than y hat, what we will have, the error will be negative. Yeah, duh. Error is negative. My pen is already, I need to buy titanium pens. All right. So instead of writing rules, we can just use this error that we produce to update our lines. So after this, we can just say, okay, what? My pen just bugged out. Instead of this, we can just write b is equal b plus, what do we have? Learning rate times the error. So if the error is positive, we increase the intercept. If the error is negative, we decrease the intercept. We don't have if statements, we don't have cases, we have mathematics doing the work for us. And this is the genius of the square trick, because the error already contains the sign that tells us what to do. If it's above, we add it. If it's below, we subtract it, and that's it. Now we can write like clean vectorized code. We can apply this to, I don't know, thousands of use cases we want. And that's not it. Let's continue. Okay. Now, let's continue. Let's continue. So, how can we use this error? How can we use this difference between the actual and predicted values? So we can adjust both the y-intercept and the slope slowly and intelligently, so it works towards creating a better predictions. So again, what's the goal? We are trying to train a linear model. We have a line, so we need to adjust. And where's the line? It's for some reason awkwardly written here, and it's quite small, but this is the representation of our line. So we need to adjust the slope and the intercept to make the line get closer to the data points, so our predictions can improve. So what did we see until now? Just a second. All right. So far, if the point is above the line, it's positive, we need to move the line up. If the point is below, the error, this guy right here, is negative, so we need to move the line down. And to move it in the right direction, we add this formula which we can also write like this: b is equal b plus learning rate y minus y hat. What is this weird symbol here doing? This n with a long leg. This is something called a learning rate, or eta, which is a relatively small number, like, I have no idea, 0.01, 0.001, even smaller. And this number controls how much we adjust the model per step. So why do we need this guy? Why do we need that? Because without it, if we don't have it here, if we just add this, we could overcorrect. The line could jump way too far and overshoot the target, and we could zigzag forever. Let me just fix this. Okay, we could zigzag forever and never converge. So we need to scale down our update. For example, let's say our price is, I don't know, 10, and our predicted value is 2. So what do we have? We have 10 minus 2, it's 8. We add b, which is the slope. I don't know, the slope can be, what can 0.5. So we add 0.5 plus 8. It would go here somewhere, I assume. So we don't want to overshoot the target, right? We don't want to zigzag. So we need to scale down our update. All right, so we adjusted the intercept. How can we adjust the slope? In those simple manual way of adjusting the slope, we said, okay, so if the point is above the line, so this is the point. If the point is above the, or maybe I can draw another one. Bam. Where are you? Where are you? Here. Bam. Is it straight? It's not fucking straight. Bam. Is this guy straight? Yeah. Okay. Wait, as a matter of fact, I don't need y-axis. I need only x. All right. Actually, let me put the y here in the middle. Okay. So let's say if the point is above the line and the right of the vertical axis, or below the line and to the left, we need to rotate the line counterclockwise. What does this mean? What does this mean? I also don't know what does this mean. When the point is above the line and to the right of the vertical axis is y. So the point is here. All right. I think I understand. So let me also draw the line. Let's say this is the line. So the point is above the line, right here, and it's to the right of the vertical axis y. So we need to rotate the line counterclockwise. We need to rotate the line like this, right? Makes sense. Where else do we need to rotate the line counterclockwise? If it's below the line and to the left of it. So it's below the line. I'm just gonna remove the point. If it's below the line, like here, and to the left of the vertical axis, same thing. We need to rotate it counterclockwise. Interesting. So in both of these cases, what do we want to do? We want to increase the slope, because the slope is related to rotation of the line. If we increase the slope, we are, okay, let me just move. We are rotating the line either here, either like this or like this. There's also another scenario where we have the point which is above, but it is to the left. Let's say it's here. In this case, we can't rotate it counterclockwise. We need to rotate it clockwise. Or if it's below the line, right, like here, and to the right of the vertical axis, we need to rotate it clockwise. Or the line should rotate down. We need to decrease the slope in this scenario. Okay. So if the point is to the right of the vertical axis, R is positive. If it's to the left, R is negative. What's R in this case? R is just X. It's the X coordinate. It's the X feature. And the actual label we can label as y. So we have the point xy. Okay, here's the trick. We can use this formula now. Slope update. Again, eta times the error multiplied by x. Why does this work? Because this error term is giving us a positive value if the point is above the line, or negative if the point is below. So it's either positive or negative, and if we multiply it by x, so the x is giving us the following. It's positive if the point is right of the vertical axis, which makes sense, and it's negative if the point is left. So if this is positive, if this value is positive, it makes sense. Look at this. I understood it. Oops, I understood it. So this is the slope update formula. So if the error value here, this is the error value. So if the error value is positive, plus, and our x is positive as well. So if our x is positive, we know that the point is here somewhere, to the right of the vertical axis, right? Oh no, I have to manually clear all of these guys. So if this is positive as well, if we multiply it, we're going to get a positive value. Otherwise, if it's to the left, if it's here, we're going to get a negative value. So what happens? What happens? When we multiply these two terms together, and again, either positive or negative, if we multiply these two terms together, the sign is telling us whether to rotate up or down. Because, wait, where's my mouse here? I have here. So the point is above and right. If the point is below and left, if the point is above and left, and if the point is below and right. All right. So if the, let's say this is the error. So if the point is above and right, what is the error? So the point, it's here somewhere, right? So the error is positive. If it's below and left, it's here somewhere. The error is negative. If it's here, the error is positive again, and if it's here, the error is negative. Okay. And what's this? What else do I have? I have the x. Same thing. Plus, minus, plus. No, sorry. Plus, minus. If it's above and left. Above and left. So it's negative. And it's below and right. Below the line and right. So here somewhere. Or even here. It's going to be positive. So the update sign will be plus, plus, plus and minus are minus, and this is minus. So what do we need? We need to rotate the line up. In these cases, oh man, I'm drawing this like an idiot. In these cases, we are rotating up. And in these cases, we are rotating down. All right. Now, can I... Let me open my Visual Studio Code. Where is it? Apologies. Just a second. Just a second. Let me open this. Where are you? Okay. Okay. So I could also write this code for this square trick, but basically the point of it is this in the end. We have two formulas and we have two rules for these formulas. So what do we have? We have the intercept formula. It's b equals b plus eta times y minus y hat, which is just the error, and we have the slope. So the new slope will be m is equal m plus eta y minus y prim multiplied by x. Basically, if we are adjusting a line by hand, the error is telling us how wrong we are, and we have the x position which tells us where we are wrong, and multiplying them gives us the correct direction. This is basically just gradient descent in disguise, because we are minimizing the squared error. Okay. This is wonderful. What else? What else do we have? There's another trick. It's called the absolute trick. So let's do this guy as well. Let's call this the absolute trick. So what's the absolute trick? It's a simplified version of the square trick. It's a bit easier to compute. It's not as precise as the square trick, but it still helps us move the line in the right direction. Again, let's write our line here. Use yellow. Mx plus b. We want to adjust our line to make it to get closer to a point, but instead of using the error, instead of using y minus y prim or the value minus the predicted value. Okay, so instead of using this, we are using something else. Just a second. Okay. We are just asking, instead of using this value here from the square trick, we are just saying, okay, if this point is this point above the line or below the line, and then we nudge the slope and intercept accordingly. There are no error values. There are no gradients. We have just signs and directions. Again, we can have a line. I don't know if I should even write it. Let's write it. Let's write this. Okay, let's write this. Why is this shorter than it's supposed to be? Okay. Where are you? We have a line. We have a line. The line says y prim is mx plus b. We have a point that is xy. We can also call these values p and r. Doesn't matter. It's not important. We want to move the line closer to that point. So we can compare, let's say this is the real value here. We can compare the real value and the predicted value. And same thing happens. We can have, if the real value is greater than the predicted value, which means the point is above the line, which means that the prediction is too low, we want to move the line up and rotate it upward. So it reaches the point. All right. So what do we have? We have again, if we are talking about the price, we will have the price per room, which is equal to the learning rate times the number of rooms, and the base price is equal to the base price plus the learning rate. Because we need to move the line up and we need to tilt the line upward. Another case is where the point is below the line, in which case the prediction is too high. We want to move the line down. We want to rotate the line downward. Same logic, only in reverse. And there is some code about this. I don't think this is very important because now. Okay, let's skip this. Let's talk about linear regression. Okay, let's talk about linear regression because we want to repeat this many times to move the line closer to the point. Okay, and I think I already started here something. Let me just make sure. All right, now this is gonna be fun. This is gonna be fun. So let's talk linear regression now. Also have some code here. Let's wait for this. So what we will do now is we will implement the simplest possible implementation of linear regression. We're gonna use stochastic gradient descent. But we won't call it directly. Stochastic gradient descent, we are going to call it differently. We need to build a machine learning model that learns to predict house prices based on only one feature, which is the number of rooms. It will do this in a following way. We will start with a random line. We will repeatedly adjust the line, and then we will use one of the tricks that we learned right now, either the square trick or the absolute trick, to move the line, to nudge the line closer to each point. And this is linear regression, which is actually explained in the most basic and intuitive way possible. Do I have... No, this is the square trick. This is the linear regression. It's also drawn. Oh, nice. I wrote this already. I don't know when exactly, but I did write it at a point in time. So I think this was also generated by tchdy. Okay, this is the square trick. Do I have the absolute trick here as well? No, I only have the square trick. All right. Adjust base price and price per room using the square trick. We have the parameters, which are the base price. It's a float value, which is the starting price. This is the intercept of the line. We have price per room, which is the slope of the line. The number of rooms, which is the feature value. We have the price, which is the target value, and the learning rate. Bam, bam. Okay. Okay, maybe we can even do a small example with this, huh? With this square trick. To dig deeper, to understand better. So what do we want? We want to train a model to predict house prices using number of rooms. So what can we have? We can have base price to be, I don't know, 100K. We can have price per room be 50K. The number of rooms can be 3. The price can be 30 320,000, and the learning rate will be 0.01. This is a small step. This is the actual price. I don't know if this is too small. It's not. This is the actual price. This is the value. This is the initial slope, and this is the initial intercept. So what do we want? We want to predict the price. If you remember, it's the p hat guy. And because this is the p hat, what do we want to do? Where are we starting? Actually, we're starting with the base price. 100K. Okay. And then we have the target. The target is this is the intercept, the y-intercept. Okay, 100K plus what else do we have? The number of rooms. That's X. That's our target value. So it's 3 times the price per room. It's 50K. So what do we have here? P hat is 100K plus 150. It's 250. But we see a certain confusion here. Our real price is 320,000 and our predicted price is 250. So we need to calculate the error. It's price minus predicted price. It's this price minus I don't want to write, but okay, 320K minus 250K is 70,000, right? And then using these formulas here, we are updating both the slope and the intercept. Okay, so if I use this formula, what is my learning rate? 0.01 times the number of rooms times error, blah blah blah. When I calculate all of this, I don't have any nerves to do this properly anymore. But if I put this guy, what have I calculated? 70K. This is my error. So if I put my guy here, 70K times the number of rooms, it's 3, so it's 21. It's 220K. No. 200,000. 210,000. 210,000. So this is 210,000. No, it's here. 210,000, and then I also multiply it by the learning rate. All right, let's do this. Let's do this quickly because I want to do linear regression. So what is the number of rooms? It's 3. 3 multiplied by the error, it's 210,000 multiplied by the learning rate, 0.01. So what will this be? I don't want to miss a decimal, so I'm going to ask Google. 21,000 times 0.01 is going to be 2,100 or 2,100. And then I have the price per room, and I just add it here. So this will now be 521,000. So this is my new price. I'm sorry if this was a bit confusing. Hopefully it's not. Hopefully it's not. So yeah, we do the same thing for the base price, and we just return it. That's it. That's the whole gist of it. But now what are we doing here? Because we now implemented something, numpy as numpy. I already have numpy here, so I don't need it here. Matplotlib. I don't need this as well. Random. I don't need random either. So I can remove all of this. And if I run all of these again, Where's my code? Where's my code? Oh. Okay. Now, this was the simple trick. Now, what is linear regression doing? We need to start with random values for the slope and the y-intercept. And then we repeat many times. That's why we have this for loop. And that's why we have something called epochs. So what are epochs? An epoch is just each iteration of the loop. And we set this number here. I'm misclicking the code every time. We set this number at the beginning of our algorithm. And the simple trick was mostly used here. Is this the simple trick? No. Simple trick doesn't work. We mostly use either the square trick or the absolute trick, which work a lot better. But square trick is more popular, so I'm gonna use the square trick here. Alright, so what is something that is used? Random. We need to generate random or at least pseudo-random numbers. Where do we generate these random numbers? Here. Because we want to generate both random values for the slope and y-intercept. And then we have the for loop, where we repeat the update step many times. What else? The random number. So we need to pick a random point on our dataset, and then on this random point we apply the square trick to move the line closer to the point. What else? We are using NumPy arrays, of course, for storing arrays. We are also using matplotlib for plotting everything. Okay, seems fine. If I run this again, wait, what's happening here? Wait. I don't want to see the history. I want only to see the points and the final line. Scatter data points. All right, so these are the labels. Point every line from the training history. This is what I don't want to do. But I want to highlight the final line. Oh, okay. Oh, okay, so these are our points. And this is our final line here. So what is here? What is the base price and everything? History, linear regression, all right. So history will be, okay, history will keep the track of our updated values. Wait, what if I print here? Print price per room, base price. Okay, so these are the random values that we started at the beginning. And as we run this method, epoch by epoch, iteration by iteration, we increase the value until we come to this point. And this point says that the price per room is 52 bucks, right? And what's the other thing? The base price is 80, so this will be I'm interested in seeing something here. Okay, so the base price is the y-intercept, and the price per room is the value we increase the slope by. Now, okay, so if I got these values, which are the direct result of training our linear regression model, so they define our final prediction equation, which is basically our best estimate of how to calculate the price of a house based on how many rooms it has. So the price per room is 52.55, which is our slope. It tells us, okay, for each additional room in the house, one, two, three, four, five, six, all the way to the 8, the model predicts an increase of $52 in price. Okay. Now the base price sells, okay, this is our intercept. It's the predicted price when the number of rooms is 0. So if a house had 0 rooms, well, of course it's not possible, but if a house had 0 rooms, it would be worth 80.82. We are most probably normalizing this, and we are talking about prices in thousands of dollars or euros or whatever. So this would be 80,000 euros for an empty flat, and then for every additional room we add 52,000 euros. So for a flat or a house that has 1 room, it's 130k, and it goes up and up and up and up and up. And to predict the price of a house with 5 rooms, for example, we can multiply this value, add the base price, the y-intercept, the slope, which is 80,000, and we are gonna get somewhere around 300,000 US dollars or euros or whatever. Okay. Now I can uncomment this. I can uncomment this code. If I run this again, it will show us historically where and how each result was. So somewhere here is most probably one of our first and random guesses, and then as we move on, we improve our predictions all the way until we reach the final line right here. Basically, this just draws some of the lines in the algorithm as we approach a better solution. I can also maybe so this is the history. I want only the first value, so let's see here, maybe the first 5 values. 0, 5. Here they are. The final learned line. Where's the final learned line? This one here. For some reason it became brown. I don't know why. Doesn't matter. So these are our first predicted lines, and this is our final. Maybe I can also comment this one out for now. Okay, so these are 5 lines in the beginning, our first guesses, which are not pretty accurate, as you can see. Now, let me just reverse this and run this all again. All is good. I don't want to print anything. Now, we can use this model to make predictions. We have a pretty good linear regression model. We can use it. And we can basically now make predictions for houses with many rooms as we want. As we said, if we have, okay, I made a mistake. I should have kept the points, but if we remember correctly, I think we had the intercept being around 80, what have I done? And the slope being around 50. So the base price is 80,000. For each room we add 50k, right? So if we have a house with 4 rooms, we're gonna say, oh, it's 80k plus 50 times 4, which is 200. 80 plus 200 is 280, which is 280,000, let's say. Okay, this is good. This was good. This was good. This was good. This was good.